Good morning, everyone. Welcome to today's session. I am excited to begin our exploration of a core concept in thermodynamics, that is, thermodynamic properties. Understanding these properties is absolutely fundamental, serving as the foundation for analyzing and designing a vast range of engineering systems, from the engines that power our vehicles to the refrigerators that keep our food fresh, and even the complex power plants that generate the electricity we use every day. Think of thermodynamic properties as the language we use to describe and quantify the state of a thermodynamic system. They are the measurable characteristics that define the system condition at any given moment. Without a solid grasp of these properties, it would be nearly impossible to predict how a system will behave or to optimize its performance. In this lecture, we are going to, on the deeper scale, into the heart of this topic. Our journey will cover the three key areas. First, we will look at the examples and establish a solid foundation for further learning. Second, we will explore the classification of these properties, understanding the crucial distinction between intensive, extensive, and specific properties is very much necessary. Knowing how to categorize the properties will help you choose the right one for analysis at the different situations or the conditions. Finally, we will touch upon the concept of thermodynamic equilibrium, a state where a system properties are uniform and unchanging over the time. This is a critical idea for understanding how systems evolve and how processes occur. By the time we conclude this lecture, my aim is that you will possess a robust understanding of how thermodynamic properties fundamentally define a system and how they exert a powerful influence on thermodynamic process. You will be also knowing the approach to solve more complex thermodynamic problems with confidence. So, with the overview in this mind, let's embark on this journey into the fascinating world of thermodynamic properties. Now, we will define exactly what we mean by thermodynamic properties. In essence, thermodynamic properties are the fundamental, measurable characteristics of a system that collectively define its state and predict its behavior. Think of them as the system's vital signs. Just as the doctor uses your temperature, blood pressure, and heart rate to assess your health, we use thermodynamic properties to understand the condition of a thermodynamic systems. For example, imagine a gas which is contained within a cylinder. To accurately describe its condition, we use properties like temperature, pressure, and volume. These properties taken together give us a snapshot of the gas state at that particular moment. Knowing these values allows us to make predictions about how the gas will respond to changes. This is incredible. This is very much important for practical applications. These properties provide engineers and scientists with the tools to analyze and predict how systems will respond to various changes in their surrounding. Will heating the gas cause it to expand? How much pressure will be required to compress it to a specific volume? These are the types of questions that can be answered by understanding and applying thermodynamic properties. Now, to make things a bit more organized, we broadly classify thermodynamic properties into two major categories. As we have seen in the previous slides, these are intensive properties and extensive properties. So intensive properties are those that can be independent of the amount of substance present in the system. They are intrinsic characteristics that don't change just because you have more or less material. On the other hand, extensive properties are those that are directly dependent on the amount of substance. If you double the amount of material, you generally double the value of any extensive property. Understanding the difference between these two categories is crucial for properly analyzing thermodynamic systems. So, with these basic definitions and classification in mind, let's now look into each category in detail, exploring examples and clarifying the concepts of each. All right, let's start with intensive property and explore what makes them so unique. Defining characteristic of intensive properties is that their values does not depend on the amount of substance present in the system. This means whether you are examining a tiny sample or a massive quantity of the material, the intensive properties will remain constant. It is an inherent characteristic of a substance itself, not the size of the system. To make this clear, let's look some key examples. First one is the temperature. Imagine a cup of water heated to 50 degrees centigrade. Now picture a bathtub filled with water also heated to 50 degrees centigrade. Even the bathtub contains a vastly greater amount of water. The temperature in both the cases is same. Therefore, the temperature is an intensive property. Coming on to the pressure, think about the pressure inside a balloon. Whether the balloon is small and only partially inflated or large and fully inflated. The pressure inside, assuming uniform inflation, remains the same, dictated by the material and the forces acting upon it. The size of the balloon does not change by changing its pressure. Coming on to the density, consider a small piece of iron versus a massive block of iron. Both are made of the same material, that is iron. Therefore, their density, which is the mass per unit volume, is identical. Density is independent of the amount of iron you have. Specific heat capacity. This is a particularly useful intensive property. Specific heat capacity tells us how much heat energy is required to raise the temperature of a unit mass, like 1 gram or 1 kilogram of a substance by 1 degree Celsius or 1 Kelvin. Because it's defined per unit mass, it doesn't matter how much of the substance you have. The specific heat capacity remains constant. The reason these intensive properties are so important is that they allow us to describe the state of a system in a meaningful way without being influenced by its size or extent. This makes them extremely useful for comparing different systems and for predicting how a system will behave under different conditions. It is also allows us to scale systems easily. Now that we have a solid understanding of this intensive property, let's shift our focus and contrast them with extensive properties, which, as you will see, behave in a different way. Now let's turn our attention to extensive properties. In contrast to intensive properties, extensive properties do depend directly on the amount of substance present in the system. This means that if you change the size or scale of the system, the value of these properties will change proportionately. The more material you have, the greater the value of the extensive property. Let's illustrate this with some common examples. Consider first property as a mass. This is perhaps the most common example. A larger system simply contains more mass. If you double the amount of substance, you double the mass. Next important property is volume. Similarly, the amount of space occupied by a substance is volume increases as you add more material. Double the substance, double the volume, assuming a constant density. The third important property is the internal energy. Internal energy refers to the total energy stored within a system, including the kinetic and potential energies of its molecule. The more matter you have, the more total energy is stored within the system, making internal energy as extensive property. The next properties are the enthalpy and entropy. These are slightly more complex thermodynamic quantities, but they also increase with the size of the system. Enthalpy is related to the total heat content of the system, while entropy is a measure of its disorder or randomness. Both of these are extensive in nature. A crucial characteristic of extensive property is that they are additive. This means that if you combine two or more systems, the total volume or the total value of the extensive property for the combined system will be the sum of the values for the individual systems. For example, imagine you have two identical containers filled with the same gas at the same temperature and pressure. If you combine these two containers into a single larger container, the total volume or the total mass and the total internal energy of the combined system will be precisely the sum of the individual volume, masses, and internal energies of the original two containers. However, because extensive properties depend on size of the systems, they can be less useful for comparing different systems directly. It's hard to compare the internal energy of a small engine to that of a large power plant. For example, because their sizes are so different, to address this issue and to facilitate easier comparison between systems of different sizes, we introduce the concept of specific properties. These are derived from extensive properties but are made intensive by dividing them by the mass of the systems. We will go deep into the specific properties in the next slides.
Now let's introduce a powerful tool for simplifying thermodynamic analysis, that is specific properties. Specific properties are essentially derived from extensive properties, but with a clever twist that transforms them into intensive properties. The key is to divide an extensive property by the mass of the system. This effectively normalizes the property, making it independent of the system set. Think of it as taking an extensive property which describes the total amount of something in a system and converting it into a property that describes the amount per unit. Here are a couple of key examples. First one is the specific volume. This is calculated by dividing the total volume of a system by its mass. That is, specific volume is equal to volume divided by mass. Instead of knowing the total volume, you if you know the volume occupied by each unit mass, that is cubic meter per kilogram or cubic feet per pound. Next is the specific entropy. It is also calculated by dividing total entropy of a system by its mass. So specific property for specific entropy is equal to entropy divided by mass. This gives you a measure of the disorder or randomness per unit of. The reason these specific properties are so valuable is that they allow us to directly compare different systems regardless of their size or mass. This is a huge advantage in thermodynamic analysis. For instance, let's consider steam. The specific volume of steam at a particular temperature and pressure is same whether we are dealing with 1 kilogram of steam or 10 kilogram of. The total volume will be different, of course, because amount of steam is different, but the volume per kilogram may not be different. So in this way, this simplifies the system design and comparison and analysis.
Let's now shift our focus to a critical concept for analyzing thermodynamic systems, that is, thermodynamic equilibrium. A system is said to be in thermodynamic equilibrium when its macroscopic properties like temperature, pressure, and its composition remains uniform throughout the systems and crucially do not change over time. Its state of balance and stability, think of it as the system being at rest in a thermodynamic sense. In this equilibrium state, all the driving forces that cause change are balanced. Things like temperature difference, pressure difference, and difference in chemical potential are all equalized. This means there is no net flow of energy or matter within the systems or across its boundaries. The system is not spontaneously changing. Thermodynamic equilibrium can be broken down into three key aspects, each representing a different type of balance. The first one is thermal equilibrium. This means there is no temperature difference within the system. If you measure the temperature at any point in the system, you will get the same reading. As a result, there is no heat flow from one part of the system to another. The next equilibrium is called as a mechanical equilibrium. This measures there are no pressure differences within the system. There are no unbalanced forces acting that would cause the system to expand or contract. The third is the chemical equilibrium. This means there are no ongoing chemical reaction occurring within the system, and the chemical composition remains constant over the time. The relative amount of different substances are also not changing. When a system is in complete thermodynamic equilibrium, meaning it satisfies all three of these conditions, it is considered stable and predictable. This makes it much easier to analyze using the principles of thermodynamics. Consider a closed container of gas. If the temperature, pressure, and chemical composition of the gas are uniform throughout the container, and these properties don't change over time, then we can confidently say that the gas is in thermodynamic equilibrium. We can then apply thermodynamic principles to understand and predict its behavior. However, what happens if the system is not equilibrium? For example, if there's temperature difference inside a container, heat will naturally flow from the hotter region to the cooler region. This heat flow will continue until thermal equilibrium is reached, with the temperature becoming uniform throughout. Similarly, if there is a pressure difference, the system will adjust through expansion or compression until the mechanical equilibrium is restored. The concept of thermodynamic equilibrium is fundamental because many thermodynamic analyses rely on the assumption that the systems are entirely or in ready equilibrium or that they move from one equilibrium state to another during a process. This allows us to simplify the calculations and make meaningful predictions about how system will behave. All right, now let's bring everything together and recap what we have covered in today's lecture. We have explored the critical concept of thermodynamic properties, which, as we have seen, are the foundation for understanding and analyzing thermodynamic systems. Remember that these properties helps define the state of a systems at any given time. We also look at the classification of these properties, such as intensive properties. These are the properties that are dependent of the system size or amount of substance. Key examples include temperature, pressure, and density. These properties describe the inherent characteristics of the substance itself. Next important property is extensive properties. These are the properties that do not depend, or we can say that do depend on the system's size. For example, the mass, volume, and the internal energy. The more material you have, the larger the value of the extensive property. Next are the specific properties. These are derived from the extensive properties by dividing by mass. This creates an intensive property that allows us to compare the different systems regardless of their size. The specific volume and specific entropy are the key examples. Finally, we discussed the thermodynamic equilibrium. This is the state where all the driving forces within a system are balanced, meaning there is no net flow of energy or matter. This involves thermal equilibrium, that is uniform temperature, mechanical equilibrium, uniform pressure, and chemical equilibrium, that is no change or no ongoing reaction in the system. Understanding these concepts, that is the thermodynamic properties and its equilibrium, is absolutely essential for the success in thermodynamics. They provide the language and the framework for analysis and designing a wide range of energy systems, from a simple heat exchanger to a complex power plants. A solid grasp of these fundamentals will enable you to tackle more advanced topics with confidence and will make informed decisions in engineering practice. By mastering this concept, you will be equipped to design more efficient engines, optimize refrigeration systems, and develop innovative technologies for energy generations and conservation. That concludes our discussion for today. Thank you very much for your attention and participation. Truly hope that this has been insightful and provided you with a solid foundation in thermodynamic properties and equilibrium. Now, if you have any questions, please drop me an email on my email address. Thank you.